Okay, welcome everyone. Thank you all for coming to February's Rust London Talks. My name's Ernest, and first question as always, who is here for the first time? Please raise your hand. Welcome, 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 welcome. Thank you all for coming. This is the Rust London Talks. It is a... Oh, sorry. This is our community meetup. It's a showcase where companies and community members get to show off what they're doing. They get to stand up here and share with us what they're working on, whether it's a personal project or something within the company, some random person in the corner who gets to tinker with Rust, gets to share their learnings with the rest of us as a community. This is one of 3 meetups or 3 community events that we hold as the Rust London community. We try to make sure that we give people the opportunity to come in and be welcomed as a new person to the language or someone who's been growing with the language since 2015. So there is also a code dojo and also a study group that happens periodically. Who doesn't know what Rust is? Okay, I will still, for the purposes of being, for not making assumptions, I'll still read out the tagline. Rust is a multi-paradigm, multi-platform systems programming language. It has great features, and it's really being touted as a piece of technology that you can really get to grips with quite quickly. There are some, nerfed, really hard edges that can get you. But as a programming language, it's really rising to prominence because of a lot of the features of the language. Here are some of the areas that Rust is being used in. Keep a special eye out for the game dev part because there will be some announcements made on that. Rust is a language that allows you to build high-performance, scalable applications in many different areas. Here are some of the companies using Rust in production. I've forgotten TrueLayer, who are our amazing hosts. We're going to hear a lot more about how they're using Rust in production today from one of their amazing lead devs, Luca Palmieri. Give him a wave. But there is a growing list of companies using Rust in production with a number of amazing use cases. Okay. So this is the London Talks. We will hold one of these each and every month, but there won't be one held next month. So March, there won't be one of these events. The reason being is beginning of April, we're going to have a special Rust London Talks Game Dev Edition. So we're going to have one of these events beginning of April, the 6th of April, where it's purely focused on game development. We're going to have 3 keynote speakers who are going to be exploring and showcasing everything going on in the arena of game development with Rust. Right here. So, all right. The details for that will be up really soon. We have a code of conduct as well. This is just to ensure that everyone feels welcomed. That's the big agenda for this community, is to make sure that everyone feels welcome. So if in any way you feel uncomfortable or you've been made to feel uncomfortable, there are a number of us now who can help address that. If I could ask Luca and Giles and Leonid and where's Jamie? If you could all please wave. These are co-organizers. So if you see any one of these people, you can approach them and they can also help you address any issues that you have. Okay. If I could ask you all to please go on Twitter and follow Rust London users. And if you're tweeting tonight, the hashtag is Rust London. If you don't fancy coming up here and giving a talk, but you still have something to share, you still have a project that you have going on, you can write a Medium blog post and we can publish that for you as part of the community. That's still a way for you to share what you've got going on, share what you're tinkering with Rust. Okay, so today's agenda, couple of announcements. I just made one big one, and then we're going to have our two speakers with a break in between. Main announcement, apart from the game dev meetup, is going to be that there'll be a few more special edition meetups coming up throughout the year. And I'm going to aim to have them all put up on the meetup as soon as the details are confirmed. So I want everyone to have an idea of what's coming up maybe 3-4 months in advance, so that you're not wondering or guessing like what's going on month to month. That's something that we're going to get better at. There's also the Code Dojo, which is coming up in March. So instead of a meetup like this, we're going to have a Code Dojo, which Luca and TrueLayer are going to be hosting. Did you want to say any more about that? Okay.
Hello, everybody. So the Code Dojo will be a learning session. So the main objective will be to onboard people who might have used other programming languages, but not Rust, or not a lot of Rust in the past, by developing hands-on a project in a guided sessions. So they're going to be mentors wandering around the room, and there's going to be a structured project to build, and you're going to be given support, and you'll be able to ask questions and just play around with the language. You can pencil the Tuesday, 24th of March as the date for the Code Dojo. We're going to finalize that more or less before the end of this week, and we're going to put the event up. So if you know anybody who is beginning, who's willing to begin to learn the language, that's definitely a good evening to join. Thanks.
Okay. Right, so now we're going to have our first speaker, Peter. If we could switch to Peter's slides. Could you please give him a big hand? He's going to be sharing with us what they've got going on at, where is it? Red Sift. Sift, sorry. All right, here you go.
Thank you so much. And yeah, thanks for having me. And thanks, Ernest, for organizing these events. These lights are very bright. So today I'm going to talk about Rust in the Linux kernel for fun and profit. We're not really hiding the fact that we're going to make a product out of this. But most of what I'm going to talk about is already open source. It has been open source for a while. My name is Peter Parkanyi, and I work as a security engineer at Red Sift. And I often troll on Twitter under the name of Rhapsody. So Red Sift is a platform company. We have a couple of products, and we built our own orchestration system around that. And there are really exciting capabilities that the platform is capable of. And we had the problem of actually monitoring this, because in 2020, containers are eating the world. It used to be the saying that software is eating the world, but the buzz today is all about containers. So just a show of hands, who is using Kubernetes? I'm sorry for you. And for the rest of you, I'm sorry because you're going to use Kubernetes in a couple of months probably. So to this question, there are only wrong answers. One of the issues with running a containerized environment is that your existing methods of tracking what's going on in your systems don't really work anymore. Monitoring single VMs is relatively easy. You just pop some monitoring software on and you look at your Datadog stats and whatnot. But once your containers are disappearing on a minute-by-minute basis even, then it gets a lot more difficult to track what's going on. So we can't really talk about monitoring anymore. We want to talk about observability. And all the things that we actually want to observe in the running state of the system So we want to know what our code does. So we're doing logging. We're looking at performance metrics to know which particular container is eating up all the RAM in the system. And obviously, there are a bunch of security metrics that we can derive from the system itself, periodic scans of the OS, and different hardening measures. If we're running at scale, we probably want to take a look at the traffic shape, how much traffic is hitting which data center, why is our data center actually going down, and why is more traffic hitting something that it shouldn't? Is the traffic taking the optimal path to be served? So what we're really trying to do is observe the state that our system's in. And as we can see, the state is complex. So in this talk, we're trying to get to the level where, I'm not sure how much is actually visible to this from this. So what's happening on this chart is we can see the end systems. These are our servers. And then we see a bunch of services that are running on these servers. And there are lines that are connecting the servers to the services. And there is another column, which is all of our files that are being accessed by those services. And in the very last column, we can see a bunch of IP addresses that those services talk to. And we can reasonably assume that those files may have been accessed by those IP addresses. And this is the sort of end-to-end visibility that observability gives us. And we can achieve this with absolutely zero configuration. We can just pop an agent on our systems and get all of this data and draw fancy charts and start debugging like which particular database Grafana is using for 10, 20, 58.6. And this is pretty cool stuff. And this is not really the sort of things that you can collect with existing tools. But there's a problem. The more code that we're putting on the system, the more insecure it gets. So we tried solving this conundrum using Rust. And it's great because Rust is memory safe. So there's a study from Microsoft that says 70% of all bugs come from memory safety. I think specifically they meant security bugs. So if we can just get rid of 70% of bugs, that's already putting us in a much better position. Rust is an amazing toolchain. You literally read the docs and it works. There's no reinventing the wheel every single time. You start a new Python project and a new Python framework. Documentation is amazing. And the documentation tools for writing your own stuff is also pretty neat and super easy. And Rust can help us achieve amazing performance. We don't need to jump the FFI gap that we need to with systems like Go. So if we look at Go and Node.js and Erlang, they are all garbage collected languages. And when we want to interface with native C libraries, then very often, well, every single time, we're hitting a performance penalty. So what these communities tend to do is re-implement all systems in their respective languages just to get a speed up. With Rust, we don't have to put in this extra work. We can just call out to C and get top performance. The other essential technology that helps us achieve this is eBPF, which looks like this. So this is one of the scary diagrams that I have in this talk. There are a couple. This is the eBPF virtual machine. It's a virtual machine that is provided by the Linux kernel. And what it allows us to do is run safe code inside the Linux kernel. So what this effectively means is that we don't have to jump the performance penalty of talking down to the kernel. We can just run code straight in the kernel without any sort of context switching, which is super important, and we'll see why. There's a special limitation. We can't store state in these programs. We have a special mechanism called maps that allow us to communicate with the user space. And these maps provide locking and synchronization primitives and whatnot in a well-abstracted way that is safe to use all the time. This is probably the top scariest diagram that I have. But it is actually scarier than what it tries to depict. This comes from a tool called BCC. So BCC is a tool chain that allows you to use and write eBPF programs on Linux systems in C. They have a wide array of programs that they have already prepared. So if you go to the BCC repo, all of these programs are already there. And they do what they do. The point is that using eBPF, you can practically hook into any part of the system. If you want to get information from the scheduler, you can do that. If you want to get information from the file system or one specific file system, you can do that as well. If you want to hook into a user space library and you want to extract information from the Java or Node or Go runtimes, you can do that with eBPF as well. The way this works is you can basically hook into any sort of function call before or after that the Linux kernel exposes. So this is pretty powerful stuff, and this is why it's important that we're not hitting the performance penalty of switching into user space and back. Under these circumstances, you can just pop some simple code that will extract information straight from the kernel that you only have in the context of that particular function and run with it. There are a couple of limitations that make this secure though. It's not Turing complete. You cannot write any program that isn't provably terminating. So there are no loops. There are no function calls. There is a limited number of instructions. Up until the latest kernel release, it used to be 4096. Now it's raised to 1,000,000. So realistically, your production systems, you've got 4096 instructions to play with, which is not a lot. And it has an LLVM-based toolchain. And it is also safe because in addition to all these limitations, you also have this thing called the verifier, which lives in the Linux kernel in a 10,000-line C file, which is called the verifier.c. And it does stuff. It's really difficult to figure out what it does unless you actually read the code. And it produces super cryptic error messages that can be fun to deal with. But like it's a special kind of fun. So where we fit into this entire stack, right? We have Kubernetes. We're running a bunch of applications in Kubernetes, background jobs, periodic things. And the agent that we made at Red Sift is sort of one leg in the kernel, one leg in the user space. We put some code in the user space using eBPF, and then we're processing whatever the eBPF code sends us back to user space in user space, and then forward it into whatever cloud we think is relevant. And obviously, because the Linux kernel runs everywhere, we want to run everywhere as well. So whether it's in the cloud, on Google Cloud or AWS, or your Raspberry Pi at home, we try to support it, which is, again, an interesting challenge. And we're trying to make this deceptively simple. But there's a couple of things going on. So we started off writing a tool chain that allows us to write C code, pre-compile it, load into the kernel on our platform, and then load the eBPF files into the kernel, start intercepting syscalls, and then pump the events out using ring buffer at really high performance, and then start processing those events in the user space. So this toolchain was fine, and we could do funky stuff like if you define your data structures that you want to send over from the kernel to the user space, we automatically ran bindgen on it. So you could use, without any sort of extra work, the exact same C structures that you were defining, but it's not C code, right? You had to use a lot of macros and whatnot. So really where we wanted to get is run Rust code right in the kernel. And during the last 9 months or so, we actually achieved this, and it looks pretty cool. This is what a basic Rust probe looks like. We define that it's a kprobe. We hook up with every single file system write event in the kernel. So in fact, if you open a file and save it, you're gonna call this function. Like no matter what program or what container you're running, and which container is accessing those files, you are going to run this function. And the container cannot opt out. We're running this on the system level. And then we are invoking some magic to store the state, and there's another handler that is going to process the state once the function is actually finished. On the right-hand side, you can see the equivalent C code. It uses, there's a laser pointer in this thing. Oh my God, it's amazing. So you can see that there are like macro calls. And there's an actual system call sort of thing in BPF where you're calling out to the Linux kernel from the BPF bytecode. So there's an additional boundary that you're hitting, and then there's another one. And then you've got a bunch of magic variables and whatnot. And you will be pleased to say that none of the C code is actually properly documented except for a .h file that you can find somewhere on the internet in some sort of Git repository. But I'm showing you function calls in the Rust code, right? So there's a lot of stuff going on. Interesting to pinpoint the proc macro. The other interesting thing is that we're getting the registers as an object that we can interact with the function call. And all of this runs in the kernel. And we have here the same sort of system, BPF system calls or BPF special calls. Another interesting example is in the same code base in our Ingraind the agent, where we are actually resolving a kernel structure, which is this dentry thing. We're resolving this into an actual path and expanding it into an actual path to then send that over to the user space. Now, this is interesting because we can do a null check on our pointer, just like any innocuous Rust code. But then also we can call functions and use the question mark operator to just quickly exit this entire code if something fails. And actually, this looks super trivial, but the initial tries to do this did not look like this. We are doing some black magic in the background where we are generating, using bindgen, some code, and then we're parsing that code back up with syn, and then generating some more code off the back of it. And we have like a dedicated C macro parser so that we can generate these function calls and actually get you high-level code. Otherwise, you would need to jump through a lot of hoops to get to the same sort of convenience that you get straight in C. But you also get the convenience of Rust's error handling, for instance. And you can like all of this is in the option monad. You can back out of a function. You can use a result as well. You can panic, which is pretty cool. And obviously, because it's inconvenient not to use loops, we can actually use loops. There are some fun stuff with loops. So if you just attempt using Rust to unroll a loop, which is basically copy-pasting the body of the loop one under the other, and then incrementing the loop variable, then it can do it about 8 to 16 times. And if you do like an early exit from that code, then the verifier is going to throw it back to you because it's invalid according to the verifier. So we've actually managed to solve this, and now we have the arbitrary limit of 500, at which point you probably run out of instructions anyway. But you copy paste the body of the loop, and that's how you should imagine this compiler working. There are hash maps. you can define them as hash maps, but they have nothing to do with hash maps. But we actually documented this and how they work, the number of entries, and you can use you know, the usual syntax that you're accustomed to. So if you would to do the same in C, you would be looking at a description like this. And I don't even know what this means. Even with the documentation that you can read up in the .h files, it's pretty complicated stuff. You get pretty simple, mundane Rust definitions here. One other thing that's interesting is the perf maps. So what the perf maps do is they basically open up a ring buffer between the kernel space and the user space. And the ring buffer, the way the ring buffer works is that you write into it on this end, and then there's another write next to it, and then there's another write next to it. And then from the other side, the user space can start reading from here, and then reading from here. And once you fill it up, you can start here again. So it just kind of goes in circles, and then you've got a couple of pointers to track it, which means that you don't have to lock this data structure from either end of the operations. And this way, we can extract like millions of events a second from the kernel. At, you know, it's going to show up on your CPU charts, but it works. And you're not hitting the limit, the performance limit of the language and the tools that you're using. Additionally, there's a thing in eBPF called XDP, which allows us to run code on the network card. So before it even gets processed by the kernel, you can run this Rust code on your incoming traffic and implement your own firewall or whatever you want in Rust and assign it to an Ethernet card, and then just start dropping packets. So what we're doing here is actually listening to all DNS queries. We know what a DNS packet looks like, and then instead of filtering on port 53, which is where usually DNS happens, we just look for whatever looks like a DNS packet and then forward it to the user space. Which is sort of the stuff that the big firewall in China does, right? Like, it's deep packet inspection. We're looking right into the packet with this amount of Rust code and making decisions whether that should pass or not. And the equivalent C code is like this, whatever it does. But actually, like, getting to this level of abstractions is hard. A couple of months ago, we didn't have strings. Now we do. We didn't have slices. We couldn't just index into kernel memory. We had to copy things out. Now we can index into kernel memory and with zero overhead start parsing up stuff that a kernel provides us in the network buffers. So whenever your computer receives the network packet, we can look at that buffer that the kernel uses before sending it on to the application that is eventually going to process it, which is pretty cool. Panics and error handling, that was a big deal. We spent a good couple of weeks on getting the error handling right to get to the level where it works like it does in user space. Loops and stuff that return early. Panics, convenient bindings to kernel headers. That was a lot of brainstorming how we should do that. And then those little situations where stuff that could possibly compile, but it doesn't really on ARM64, but it kind of does on AMD 64, unless it doesn't because you have a weird version of the compiler. So this is the sort of stuff that, you know, like it's a Heisenberg. It just sometimes happens, sometimes doesn't, and super, super difficult to nail down. But now, luckily, we're at the stage where we're running all of this in production, and we have a pretty thorough CI around it. So we know that this works on Raspberry Pis, and we know that this works on ARM64's, AMD 64 servers, and we know that it runs on Google Cloud and AWS. So yeah, this is the Rust part, and I would like to shout out to Alessandro Dessina, who was pretty essential to making this happen. His work has been amazing, and He's probably the #1 expert on loop unrolling at the moment, and he's actually looking to contribute a lot of this upstream to BindGen and LLVM, and we're trying to work out how to do that. So if you want to take part in this, then we're hiring in our London office. And we have a lot of plans on where we're taking this and what is the stuff that we could possibly do with it. And there are a number of links. Elixir.bootlin.com is basically the definitive space to explore the Linux kernel and what's going on inside and navigate the data structures. And then we have a pretty thorough API documentation. So everything that you can do in the eBPF world, we've documented it and as a Rust doc. So it's a type-safe documentation that you can navigate. And as far as I know, this is probably the most thorough documentation of the eBPF world that is available at the moment. And then obviously the projects, there's a library that is Apache MIT, and then you can use it straight away. But because of licensing limitations, the actual agent is GPL. So thank you for listening, and I'm happy to answer any questions that you might have.
Thanks. Can you hear me? Yeah, cool. Yeah, thanks for the interesting talk. I wanted to ask, I didn't quite understand how exactly the compilation step works and how you get it to actually run in the kernel. Do you just compile it with cargo, or does it recompile C somehow? I didn't quite get that bit.
So we do actually compile this with cargo. We use build.rs to modify the build process and build the bindings and whatnot. But in the end, it's we have a tool called Cargo BPF, which helps you set up a project and helps you integrate this entire workflow with Cargo. And then Cargo BPF can actually load your modules as well. But yeah, so it's pretty much integrated into Cargo. And the way that it works in Ingraind is we have a specific crate. And that specific crate is containing all our BPF modules as separate binaries, and then we build each of them as a separate step.
All right, you going to catch it? Here we go.
So you talked about a lot of things like loop unrolling and using the hash maps. Where was that kind of mainly implemented? Have you done it at procedural macro level, down more in the LLVM? There's a lot of transforms going on, and I'm kind of curious where they exactly live in the kind of modifications you've done to the Rust stack.
So a lot of the APIs are actually wrapping C APIs. There's a lot of unsafe code that we're hiding, and we've made safe and sound wrappers around them. And there was a lot of, we actually got a lot of harassment for some unsafe stuff that we've done, which aren't actually unsafe because they wouldn't work anyway. And they aren't unsound, sorry. But yeah, they are basically safe wrappers around the sort of APIs that I've shown you. And the same thing exists in the user space as well. So you have pretty similar structures on both ends, but they are actually separate implementations.
I was more kind of interested in like the hash maps, because the hash map's not actually a hash map in that case. How is that kind of?
Right. So the hash map is implemented in the kernel, okay, and it's provided by the kernel, and all the functions that you need to call to interact with the hash maps are either a system call from the user space side or a BPF call, like a VM call that the compiler will emit. Currently, only LLVM is aware of all of this. So if you write that special function name in LLVM, then it's going to compile it for you for the right sort of function call. But that is basically the only function call that is permitted that goes through the VM binary. And it's emitted as an opcode in the VM bytecode.
Thanks.
So relatedly,
you said there was work that needed to go into to implement things like slices. Where was that work? Was that LLVM or something else?
Yeah, so
and also panicking. I was wondering about that.
Yeah, so panicking, yeah. So these are two stories. So one of them is the slices. The problem with slices is that there's what you can call, there's what we call an aligned access to memory. And under certain circumstances, the structs that LLVM generates are not aligned. And this causes a problem on certain architectures, but not always. So we had situations where the code that LLVM generated worked just fine on my computer. It worked just fine on the CI, but when I dropped it onto the Raspberry Pi, the verifier complained because ARM, the same code wouldn't work on ARM because of the restrictions of the ARM CPU's memory accesses. So we worked around this by and actually, I think this is tied in with the panic handlers. So the panic handlers were a special kind of code. So every single slice access has a panic code associated with it, because if it's out of bounds, then you need to panic. So we had to go through this, and once we solved that panic thing, where we basically, I think we're basically rewriting the LLVM bytecode. Whatever it generates, we're stripping out the parts that LLVM compiles there and replace it with our own handler. Once we solved this, then suddenly slices started to work as well. Yeah, so this is how these are tied together. But it was a journey of discovery, right? So the very first instance, I was writing programming 101 style code where I would set variables in Rust outside of the loop just so I can check after the loop, so whether I need to exit or let the packet pass, which is hilarious, but that was the only way I could compile and insert it into the kernel. And then we figured out why. And then we came to the slices part and we figured out how that's gonna work. There's a lot of LLVM bitcode and like IR and BPF assembly involved in this kind of stuff, which is fun. After a while, it's like in the Matrix, like the code starts disappearing and you just know what's going on, but I wouldn't recommend it.
I actually have another question. What are the pros and cons of eBPF versus a kernel module? Because you could probably do this in a kernel module. You wouldn't have the safety, of course, but you also wouldn't have the kind of the problems you've had to solve to get to it.
So I'm aware of some Rust efforts to build kernel modules. The benefits of LLVM is that it cannot possibly crash your kernel. A kernel module can. So there's a trust problem when you're inserting random stuff into your production systems just to try them out, what's going to happen. And if you're inserting XDP code, then you can still block off all network traffic. I was debugging for like an entire night why my network cards aren't working, and when I rebooted, everything started working, and it's like, oh shit, I left an XDP probe in. So like this kind of stuff happens. More interestingly, most of the time when you're building kernel modules, you need the full source code, and it's going to work with that particular kernel only. With eBPF, you can get away with loosely building to something that's more or less compatible. I think on our production systems, we're basically building for a completely different kernel version that we're running on our systems, and it still works. And I didn't even realize until I checked like recently on the CI, like what is even going on. So I think the safety angle is super important. And obviously, it's so much simpler. You don't need to interact with the kernel at all.
Yeah, cool, thank you. Any other questions?
Anyone else? Any other questions? Okay, thank you very much.
Cool, thank you so much.
Okay, we're going to have a quick 10-minute break, and then we'll be back with our final speaker.
Cool, nice talk, really interesting. I could have had more, but I didn't want to. I felt like I was hogging. So I must win some stage.
If he doesn't come back.
All right. Hello. Hello, everyone. If I could ask you to all to come back, please. Hello. If I could ask you all to take your seats. I don't know what's wrong with me today. I'm like nerves all over the place. Oh. Okay. Yeah. Just waiting for the last few. There are seats on the bleachers, and there are a few seats dotted around if you want to take a seat, get cozy. Yeah, okay. Right, so next speaker is Luca from TrueLayer. He is going to be giving us a talk on some of the amazing things he's been doing. And yeah, let's give him a hand.
Thanks, everybody. Good evening. We're going to chat about writing enterprise software. So I'm going to walk you through what it feels like to develop a fully working, not super toy project, backend service using Rust. My name is Luca. As Ernest says, I work here at TrueLayer, so I'm playing host tonight. I'm also one of the co-organizers of the Meetup. And I'm a lead developer, but in the Rust community, I maintain a bunch of open source packages concerning scientific computing, numerical computing, and so on and so forth. Now, Ernest, do you have the pointer? Cool, much better. So just to get a sense of the audience, how many of you develop backend services of any kind? Nice. How many instead have done front-end or full-stack type of work? Still a solid 50%. Okay, so this is going to be relevant. Good. Cool. Not so much. Perfect. So first of all, what I want to get clear is what do we mean by enterprise software? Enterprise software used to be a term much more common, I think, 10 or 20 years ago in books and articles and resources. And in general, what I define as describing as code somewhat complex systems that are made of many different parts that need to work together to achieve a certain kind of outcome. In a nutshell, we can define enterprise software as the art and craft of encoding and formalizing processes as code. They can be business processes, they can be other kind of processes. It's somewhat a complex activity that we need to automate, partially, fully, or substantially. Which means that in a way, enterprise software developers are bureaucrats, just version 2.0. They just take rules and encode them. Instead of making them into laws, they make them into programs. But there's a bunch of additional complexity, and that's what we're going to talk about. So what are the challenges? The first one is that that process, that business process, for example, is usually aimed at doing something, unless it's one of the bad ones. You want to produce some kind of outcome, and that means that you need to understand the domain in which that process takes place. So if you are building, for example, accounting software, that you probably need to understand the domain of accounting. You need to understand the relevant laws, you need to understand the relevant documents, you need to understand all the people involved and what they need to do to actually make this process succeed. The same happens if you work in healthcare and you're automating, for example, or working for hospitals and writing software that nurses or doctors uses. There's always some kind of domain knowledge that you need to understand, study, internalize, and that you can actually produce software that does a subset of that function. The second thing is that processes are not static. So even if at a certain frozen point in time, you understand 100% of a process and a domain, that process is going to change over time. And generally speaking, you don't want to throw away the code you wrote. You want to change and evolve the piece of code so that it can fulfill the new requirements, unless that process is under 50-degree change, and then you write new code, in the best case scenario. The second thing is that in most cases, you will have different expertises who need to work together. there might be different programmers who might have experiences in different parts of the stack because the system is very complex and you need people to cooperate with each other with their own expertise. But most generally, that will involve people who are not technical, and you will have to work with them, being them domain experts, people who relate to clients and customers, or generally people around you that you need to cooperate to make this process work. For example, users. And lastly, but not less important, people come and go, the code stays. In the best case, if you wrote something that is useful, stays in production somewhere, which means that other people will have to pick it up, will have to touch it, will have to evolve it, and that code will have to be in a state which allows them to do so without wanting to throw themselves out of the window. So in general, if we want to express what do we need from enterprise software code, we like it to be correct. So we like it to do what we believe it has to do. So understand and obey some kind of spec, more or less explicitly defined. We want it to be expressive, because if someone needs to pick this up, they need to understand the domain that that code touches. So it's not enough to just understand the sequence of commands that that code encodes. We actually want to understand why it was doing what it was doing. So trying to encode as much of that domain inside that code so that you can learn it by just reading it. And we also want it to be supple in such a way that it can evolve over time. I chose supple instead of flexible because you can never be flexible in any direction. You can always choose to be flexible in certain directions and not in others. And you need to understand the domain and have a little bit of luck to have chosen the right directions. And lastly, but that's still relevant, yes, it should also be executable by machine because it's code and needs to be, as much as possible, part of an automated process. Where does Rust fit into this larger picture? The thesis we're going to chat about tonight is, can we use Rust to build enterprise software? And why is Rust a good fit for it? I'm going to just enumerate a bunch of properties that might make it a good fit. First of all, Rust is a very powerful type system, one of the most powerful out there if you are not into functional programming languages like Haskell and the friends of Haskell. The type system is extremely useful because it allows you to encode a lot of structure into the way your code is architected, which makes it clearer of the intention behind the code you're writing, and can also make sure that certain types of states which are incorrect according to the domain simply are not possible because they will not compile. It has great modularity, both in terms of support and modularizing code in the module system, and in terms of factorizing functionality out and making sure you can reuse pieces of code, in particular traits that you can implement on structs you do not own, on foreign traits that you can implement on structs you own, which is much more powerful than just subclassing for classes you own. There's a vibrant community. So as we said before about enterprise software, you will have to talk and interact with a lot of people. And that is also true when you're writing software. You will have to interact in many different ways with the community behind that software. And understanding if that community aligns with what you want to do is a big part in choosing if you want to bet or not on a certain type of technology. Last but not least, it has solid tooling, which makes it much less painful to start out a project, to pick up code written by somebody else, just be productive in doing what you want to do. I put in gray and kind of a little bit hidden the Rust has great performance, because for writing enterprise software, unless you're doing something extremely successful and you have millions of users, that's generally not a concern, or less of a concern than actually getting it right and getting it out as quickly as possible, as correctly as possible. That it's nice that Rust doesn't consume a lot of resources, it's nice that it has a nice performance profile, but most generally, you will address higher scalability requirements by having a different architecture or just scaling out your services. So it's not C or Rust who's going to save you. So you might or might not be convinced that all the reasons I enumerated are good. Some people are. But most cases, this gets received using this sentence. Rust is great, but. And that comes from that enum on the right. So Rust is great, but it's too new, which means that it's a risk because it's shiny and new and has not been tested in production, so it's not been proven by the test of time. Rust is great, but it's too difficult, which means it's going to be challenging for people to pick it up, which means it's going to be challenging for people to be productive. Rust is great, but it's not for enterprise because of all the amazing talks and resources that people push out around Rust being a system programming language. Most people react saying, we don't write databases. And last but not least, Rust is great, but there are few engineers. So if I want to build a huge company, I will not have enough talent to actually attract and hire to do whatever they want to do. Now, we could address all of this in a 2-hour talk, but for the purpose of what we do tonight, we're going to chat about Rust being actually very good for enterprise. So, how do you de-risk a technology? Generally speaking, when you want to pick something new and shiny, and you want to use it for something serious, aka enterprise software, you need to show that it actually can fly, without actually flying, because flying takes a lot of time and preparation, and you don't want to invest so much if you don't know you're actually going to do it. So you de-risk it. And the way you de-risk something, generally speaking, in the world of software is by building a toy project. But you don't want it to be too toy project, otherwise it's actually useless. In this case, what I worked on together with another person is the real-world specification. Real-world, as the name says, is not such a toy project, and the tagline is the mother of all demo apps. So what real-world is basically a spec. Real world is a clone of Medium, so it looks something like this. You have your blog post, you are a user, you can sign up, you can sign in, you can comment other blog posts, you can follow other users, you can delete comments, delete articles, publish articles, and do all the things you would generally do on a blogging platform. So it's not super trivial. They publish a spec, which is an OpenAPI D3 spec, which define what those endpoints look like, what they get as request parameters, what they expect as responses, what those endpoints are, if they need to be authenticated, and what the errors should look like. And a bunch of different people go around and implement this spec for different languages and different frameworks. So you can find backends implemented in Node, Go, ASP.NET, Django, Python, Laravel, PHP, and so on and so forth. And also multiple frameworks for the same language. If you look very closely, there's a bit of Rust down there. There's just some called Rust, that's Actix. There's another one called Rust Rocket, which uses Rocket for the API. And there's also a bunch of front ends which use that API instead to implement the visual part. And you can basically mix and match. So what we set out to do was real-world tied. So taking the real-world spec, implement a new backend API for it, using Tide as the web framework, and Rust, of course, as the programming language. So, what does it look like? Nothing particularly innovative here. So we're looking at a backend application, and we're using a 3-tier architecture. So we're going to receive requests from the internet, that fluffy cloud on the left. They're going to come as REST API calls. We're going to handle them in a web layer. The web layer is going to use Tide as the web framework to handle all the HTTP-related stuff. Then we have a domain layer which contains the business logic, so the stuff that is not technology dependent. It's just how we go about dealing with this domain of creating and managing blog posts. And then we're going to have a persistence layer which deals with the database, so where we store stuff for it to be persistent across requests and across restarts. That is done using Postgres, so a relational database, and we use SQL, Diesel as a ORM. And we slowly go through each of these layers, understanding what they mean. Each of these layers is also a subcrate. So the project is structured as a workspace, and each one of these can be picked up independently. So if tomorrow you want to implement the real-world spec, but you want to use another Rust web framework, keep the domain layer, keep the DB layer, swap the web layer. You want to try another ORM, keep the web layer, keep the domain layer, swap the DB layer. So this has been developed as well in order to make it easy tomorrow to showcase another framework or showcase another ORM. The domain layer doesn't do much, but you can keep it. So how does this work? Persistence layer. So how do we keep the stuff in the database? ORM. So as in most programming languages, where you interact with some kind of relational database, you don't really want to be mapping the response manually into objects or structs or whatever is convenient in that programming language. So you use an object relational mapper, which does that dirty work for you. In our case, that is Diesel. So this has been around in the Rust community for quite some time at this point, and it's fairly polished. So that's very good documentation on the website, and in general, it's very easy to find answers to your questions, either in the docs or the website, or just random people on the internet. So, ORMs. When you're actually running a production application of any kind, doesn't matter how good you think you are at the beginning, your schema will have to change over time. So the first requirement is, how do I handle SQL migrations? Diesel provides you a CLI, called this a CLI, which lets you manage migrations. So every time you generate a new migration, you get predefined down and up script. The up script is to execute the migration. The down script is to roll back the migration. Diesel takes a SQL first approach, which means you define your migrations as SQL queries. There's no Rust whatsoever. So if tomorrow you want to migrate to something else, you can keep the same migrations. And Diesel is then going to generate automatically a Rust representation of those tables. This is going to be done at compile time, and you're going to get this fantastic table defined using a macro, which means that now there is a Rust representation of what that table looks like, which means that Diesel can perform compile time checks on a lot of different things that you're doing with that table. So every time you're doing a query, every time you're performing some kind of manipulation, Diesel knows what the types of each of those columns are. So it will not allow you to compare an integer with a string, because that makes no sense. It will not allow to run scepter operators on certain data types if they actually don't make sense, which is fairly convenient, which means that you know at least syntactically your queries are correct. Then, of course, if you're doing the right thing or not is a different kind of concern. As all ORMs, it provides you with a query builder. So if you want, you can go in there and run pure SQL if the query builder doesn't suit what you need to do, because you need to do some fairly advanced query. But generally speaking, for most simple CRUD operations, you will have some kind of statement. In this case, it's an update. We are updating a user, so we're getting the updated value as a details variable into the function. We're firing an update statement on the user object that we retrieve from the database using the ID. We say what we want to set. We get the result passing in the connection to the database. And this returns a result, which means the operation can succeed and we get a user, which is going to be the updated user, or it can fail and we get some kind of error. Now, so far, all shiny and good is also good and healthy to say where stuff is not so nice. As we said, Diesel does a lot of stuff at compile time to make sure that your program is correct and to auto-generate schemas and do all sorts of checks that make you sleep safe and run code in production. At the same time, this also takes a lot of time. So if you compile from scratch the DB subcrate, and you use this very handy -z timings feature, which is going to plot what each of the crate in your dependency tree is taking to compile, you will realize that Diesel takes a fairly large chunk of that. So it's, what, 25 seconds out of 55? This is a clean build, so you don't do this every time you're building your project. The first time you build it, then you're going to do incremental builds, and they're going to be much faster. But if you have a very large project, this can become substantial. So it's something to keep in mind. There are other ORMs or SQL wrappers that you can use in Rust if you don't want to use a full-blown ORM like Diesel, and they're generally much faster to compile. Now, the persistent layer works using the principle of inversion of control. So in the domain layer, you define a trait called repository, which just enumerates in the language of the domain what kind of operation you want from your database. So in this case, we want to be able to find articles, to get a feed, to delete an article. We don't define how those operations are going to be performed. We just say what they are and what the signature looks like. And then any kind of DB layer can implement those operations for a specific database, which means that if you want to swap, for example, in your test suite, using a mock database, like an in-memory store of any kind, you can easily do so and mock out the repository trait, which makes it fairly convenient to do tests one layer at a time, slowly working your way up to the HTTP layer. So you have your repository and your persistent layer, then you work up and you have your domain layer. Now, the big deal in the domain layer is type-driven development. So it's being able to leverage type system to make it so that incorrect or just erroneous state is difficult or impossible to represent. So encoding the constraints of your domain as type level constraints. There's a lot of literatures and talks and resources about doing this in different language communities. There's a lot in F#, there's a lot in more functional languages like Haskell and OCaml. So I've just put down some links which are going to appear again at the end. I'm just going to give you a very fast walkthrough of what this might look like on some simple examples, but it's definitely a lot to learn. So first thing that is, I think, one of the most refreshing things you find when you start programming in Rust is that you can have your cake and eat it too. So there's generally two approaches to mutability. You either are a purely functional programming language, which you say, I don't mutate anything, anything is immutable, and then you need to kind of manage things using different mechanisms and recursion and so on and so forth. Or you embrace the fact that anything can mutate everything, and every time you're passing something to a function, you don't really know what is going to happen to your argument. Rust gives you a little bit more control, which means that thanks to the ownership model, I know that when I call the slug method on my article content, is actually not going to touch my article content because it's taking it as an immutable reference, which means that if I'm scanning a large piece of code, like a complex method or a complex function, which is calling a lot of different sub-functions, I can be fairly confident, just looking at the signatures, that if my arguments are mutating, I don't have to check all of them. I can only check the ones that take a mutable argument, go in there, understand what the code is doing, and pop back. It makes it much easier to read code. And as we said at the beginning, the code is most often read than actually written, and many different people will have to read it. So the easier it is to read, the better it is. Secondly, which of course is a more general argument, you can use ownership semantically. So it's great that ownership can be used to track memory usage, and of course that's the primary concern of it. But you can use it in domain layers to actually express what things mean, what's your intent, what you're trying to do, some kind of manipulation. So let's look at this small snippet. We have a struct called password, which just wraps a string. So it's a new type. On that password, we implement a constructor called fromClearText, which takes, obviously, a clear text password as argument. What we're trying to do here is make sure that when we ingest a password that we're going to store in the database, we're only going to store hashed passwords. We're never going to store clear text. What do? In a repository, we take as argument of the set password or create user a struct that has a password as a field password. And the only way you have to create a password is going through that constructor, which is going to hash the clear text function, the clear text password. So it's technically impossible for you to save in the DB a non-hash password. And given that fromClearText consumes clear text password, because it's taking a string by value, so it's moving the ownership inside the function, you will have to explicitly clone it to actually keep the clear text password around, which will at least make you think twice about what you're doing and what you're doing with that password. And this is just a very trivial example. You can do much more using ownership a little bit creatively. And to reiterate on what we've been saying already, up to a certain extent, you get very meaningful signatures. Just by looking at the signature of a function, you can tell a lot about the way it behaves. So in this case, we're looking at the publish article method on the repository. It takes the repository itself, which means it's using the connection, but it's not modifying it. It's taking the draft as move as value, which means it's moving the ownership of the draft inside the repository. And that's because we're converting a draft into an actual article. So we are transforming the draft and consuming it. The draft will have to be written by somebody. So we're going to take a reference to a user who's going to be the author of the article, but nothing is going to happen to the user. We're taking it by mutable reference. And we know that this method can fail. So we can either get a published article, or good, on the OK variant, or if we get an error, we're going to get a publish article error. And then we can go and look at the publish article error and actually see in what ways that function can fail. If you have been programming in languages who have exceptions, I'm quite sure you've wrote code in like try-catch statements, in which you say, well, I handle all the possible ways in which this can fail, just to find out later on that it was actually another way you didn't consider, and that bubbled up and did something you didn't expect. That just cannot happen. Worst case scenario, this function panics, but you don't recover for panics unless you're doing something specific, unless it's going to fail, and then you know what it fails with, and then you can handle that. And the compiler is going to make sure you handle that. You cannot just have results laying around. Which leads us to errors values, which is another very interesting pattern that you have to use when you're doing domain design. It's just clearly specking out in what ways things can fail. So let's look again at this function. We said it can fail with a publish article error. What does that mean? Is it easy now? It means it can fail in 3 ways. We're using this error just to make it more convenient to define error structs, but you could do the same without macros just by implementing the trait yourself. It can fail if the author is not found, and we're going to print a very nice error message saying there is no author with this user ID. We're going to capture the underlying error that we're going to get because we're calling another function. And we're also going to capture the UUID so that we can report it to the actual user who's calling the route. It can fail because the slug is duplicated. So it means that the title is leading to a slug, which is not unique. Or it can fail because something went wrong in the database, and that's just bubbling up an exception which is coming up from the database layer. But it's opaque. We don't let the user expect it. So we also have control over what passes through the different layers of the application. And this is pretty much enough for the domain. Last but not least is the API layer. So the API layer calls inside the domain layer. So the domain layer defines commands, which basically tell, this is the way you can use me. This is the functionality I provide you. And the web layer just needs to convert HTTP endpoints and calls into calls to those commands. Nothing more, nothing less. If tomorrow you want to give another access point to your application, for example, a CLI or a UI, that you could just swap the web layer and directly call into the commands using whatever other type of interface you want to use. Actually, so the web layer uses Tide. So Tide is a web framework that has been around in Rust, I think, for a year at this point. Was originally developed by the Rust Async working group and has then since moved to the HTTP RS organization, the same that is developing Surf and Async Stud. It's still not production ready, but is fairly friendly and is very similar to other micro frameworks you can find in other programming languages like Flask or FastAPI. And it's fairly easy to get started with, but you could as well do this with Rocket or Arctix or whatever you think is most useful for your project. So if you're writing APIs, in particular REST JSON APIs, the first thing you're going to do over and over and over again is serializing and deserializing data. We could actually go as far to say that most microservices spend 90% of the time doing that and 10% doing something else. Rust is very good libraries for doing serialization, deserialization, in particular serde, so serializing, deserializing. You have a struct, you are notated with a procedural macro, which is serialize, then you can magically serialize it. And you're notated with deserialize, you can magically deserialize it. You have a bunch of other attributes you can use to customize the way that serialization, deserialization works. In the spec, we wanted fields to be camel case, so we annotate the struct with serde, rename all camel case, and serde will do that conversion for us. And also will provide us with useful errors, describing what is missing, and so on and so forth. And then you can use traits, like the from trait, to express in a very uniform way the shimming layer between your API types and your domain types. And if that conversion can fail, you can use try from, which allows you to express the fact that it can fail and in what way that can fail, which is once again an instance of parsing dot validating. So instead of building your domain struct and then check that it's valid, just make it so that you cannot build it if it's invalid and capture that inside an error. State management is another big one while you're writing APIs. So how do you manage all the things whose life cycle is longer than a single request? In this case, considering the application, the only thing we actually want to store in here is the database connection, which is our repository. The repository, we don't actually specify what that is. So once again, we are generic over the actual implementation of the database connection and the repository trait. Just say, give me something that implements repository, and then I'm going to be able to do everything I need to do. Which means, once again, that if you're doing testing and you want to test your application without involving the database, you can do so by passing any memory database on any other kind of mock. Then, how do you actually instantiate your application? You have a function, get up, That's just the way I do it. You pass in the repository, you construct the context, and then you just start a server. On that server, you can add middleware, you can add routes, and then you can just run it, basically. Each of the endpoints looks something like this. So it's an asynchronous function. Yes, Rust has async await. It's fairly convenient to use. It's an asynchronous function, takes a request as an input, which contains the context. So from the endpoint, you can refer to the global context. You can do any sort of manipulation, and then you return a result, response, or an error response, depending what happened. You can retrieve the state from the context just by doing context.state. And then this context is struct, and we retrieve the connection to the DB. Routing, what does this look like? So you have your API object, is the one we got at this point. So you can go in there, and you say, well, at this route, mount this handler. So you're going to say @/API/user, that you're going to use an HTTP verb, in this case, get. And then you're going to basically pass in a function that is going to handle those requests. Now, tied at this point in time is a little bit limited in the sense that it doesn't allow you to return result from an endpoint. You're supposed to return directly a response, but that's going to be changed fairly quickly, and I just shimmed it in such a way that I always convert the result into a response before actually returning. So that's why you see that little closure there using async move. And last, but once again, definitely crucial, you want to be able to test your API from the outside. You want to be able to interact and test your API without knowing anything about what is happening inside it, often called black box testing. You can do that. It's fairly simple. You just create your application, which is here. Then you use HTTP service mock to actually spin it up and make it so that you can make calls, and then you just start it. And you can interact with it in your test suite by doing server, simulate, you pass an HTTP request, you get a response out. And you can make all sorts of assumptions over that response. Wrapping up, Rust as definitely a newer language, is definitely new in the backend service space, but there's actually a lot of libraries out there who are very high quality, who a lot of people have been putting time, sweat, and blood into, who will cover 90–95% of your use case out of the box without you having to do anything. And it will actually be fairly simple to cover the 5% that is missing, either by contributing upstream or just by writing the glue code that is necessary. And it can give you a lot without going into more exoteric languages that otherwise you wouldn't have been able to use anyway for enterprise software. So I hope the talk was useful, and this stimulates you, if nothing else, to try it out and see what that looks like, or what that might look like in a new project or in a small, new, non-production critical application. And all the code I've showed during the talk is available on Github. So you can go real-world-tied, and you can just browse through the repository. You can look at everything that we did together with Colin, who is the other one who started the repo. And if you want to make it better, contribute, that's welcome. We're currently adding it to the real-world repository as one of the supported backend. So if you want to leave a star and get that a little bit higher, that's also appreciated. And if nothing else, thank you. Any questions?
Right. Just want to ask you a little bit about really another debate that goes on, and that is regarding the LAMP stack, that is Linux, Apache, MySQL, PHP. And it's just related to what you said earlier about the debates for and against Rust. There are those who argue with a LAMP stack, like PHP, that one should be using them because, amongst other things, I think it's fair to say most, say, website software and other stuff is written in that. Equally, say, PHP has received quite a bit of negative publicity as well, or negative debates on it. So I was just thinking, your decision to use things like say, Diesel and Postgres SQL, did you consciously take the decision to avoid LAMP stack or any other, say, stack like that? Or did you simply just say Diesel and Postgres SQL because they just happen to produce the best results?
Okay. So even though it might look like the contrary, I very much like boarding technology, in the sense that when you're starting a new project, it's cool to try something out. It's called innovation token. So you say, I'm going to try something new when I'm doing this. But for all the rest, I'm going to use something that I know it works. If I were, and I do this at work on a daily basis, if I need to start a project and I need some kind of relational database, I know that Postgres is a solid choice, and it's going to have my back for a long way, unless I'm doing something very weird. So that's why I chose Postgres as a state persistent store. At that point, when I was looking at ORMs, Diesel is actually the only one who actually represents the classical vision of an ORM. So I picked that by default because it's mature. And I tried Tide because I wanted to try something different. But that very much doesn't mean that the rest is not good or not useful. I mean, millions of dollars have been done in more exotic languages than PHP. So use that if you need it.
So I noticed that you briefly brought up async standard. Is the stack you built built on top of async standard or Tokyo? And is this a deliberate choice or just something chosen by your dependencies and frameworks that you use? And if it is a deliberate choice, why did you choose one over the other?
So when you're using Tide, of course, Tide brings in async stud because that's the framework underpinning it. So you get that out of the box. Initially, we were running Diesel on some kind of thread pool and doing some stuff with the Tokyo executor. I removed that just for the sake of simplicity. I don't have strong preference either way. I've been writing code in different projects using both async stud and Tokyo. I think that async stud is easier to get started into if you are starting asynchronous programming in Rust. So it's definitely something I would recommend for a new language learner to pick up if they want to do asynchronous programming. You can do amazing things with Tokyo, and there's amazing software running on Tokyo. And I would like to get to a state in which one can be abstract over the executor. But unfortunately, due to some misalignment on some traits, on the futures traits, this is still not possible. But I would very much like to get at that point in time. So, of course, this is not a production application. So I haven't been going there like benchmarking the microseconds to know if one executor gives me more performance than the other. That's definitely not the focus here.
Anybody else?
Yeah, almost. So what I was thinking about when I was watching this is that this is pretty much what I would do in Java. And we're not really gaining any, like we're not having less code than we could have in Java. We're not having necessarily more guarantees that we could express there, although arguably we get more. So in your opinion, is there a toolkit that would allow us to cut down on the sort of enterprise noise that is introduced by the three-layer architecture in Rust?
Yeah, definitely. You could have stuff around that generates macros, that does things. You could have that as a framework, which of course doesn't live in your code base. You could just express the stuff you care about. Then of course, the amount of boilerplate you want to use and how heavy you want to go on the architecture very much depends on how complicated your project is. So if you're doing something that is not very complicated, probably a domain layer is an overkill because you can just handle that inside the handler. Different problems, different solutions. I would argue that you get a little bit more than Java. I haven't been using Java directly. I've been using mostly C#. And there's a lot of things that you get in web system or Rust that you don't get in C#. Traits make a huge difference, and they're much more powerful than interfaces for a lot of use cases. Algebraic types give you a lot when you're trying to express state machines, and you don't have those. So there are new things that you don't have there. Of course, the underlying type of software you're trying to write is very similar, so you're going to use similar patterns. Then how concise that is going to be depends on what we use. We could have frameworks, but it's nice to show the stuff without any magic around it when you're presenting, and that you can actually do a little bit more of a Rust on Rails, if that is more or less the goal, which would be very nice to have, by the way. Thank you.
right, so that's pretty much it for this month's meetup. Again, thank you all for coming. There won't be a London Talks in March. There will be a Code Dojo hosted by Luca here at TrueLayer. I'll have the meetup page for that up as soon as possible, and also for the Game Dev London Talks in April. Again, thank you for coming. If anyone's looking, TrueLayer are hiring, as always. And yeah, sorry? And Red Sift as well, right? Okay. The pub is the Harlequin, right? The Harlequin round the corner. So we'll all kind of congregate at the front entrance, and then it's a 5-minute walk just past Sadler's Wells. So look forward to seeing you in April. And whoever wants to come to the Code Dojo, there'll be limited amount of spaces. Be like, how many people? 20, 30 people. And it's, again, designed for people who want to get started with the language. So let's go to the pub.
Is the workshop sold out?
The workshop, yeah, the Ferris Systems workshop sold out. Yeah, so anyone who is interested in Florian Gilcher's workshop, that's pretty much sold out now. So it's been an amazing response from people. Yes. Yeah. It's been an amazing response from people who really want to get up and started with the language. They will be holding more. They'll be coming back from Germany again to hold more London workshops because there's an appetite for it. So now let's go to the pub. All right.